everyone. So I'm just going to talk about a set of controlled mosaics that we've been working on with the LROC team at Arizona State University. So everyone should be familiar with these 13 candidate landing sites. If you weren't before this, hopefully you saw Angela's talk and now you are. But what we really want to do for each of these sites is take the NAC images and then, make sure they're accurately located on the surface, but also, maximize the illuminated area, but without kind of introducing sort of wild shifts in illumination geometry from image to image. So these are kind of our main steps that we use. I'm going to get into those in more detail, but I kind of want to point out this mosaic. This is one of our completed mosaics of Fustini Rim A. You do notice that there is a couple different illumination angles in here, but we've tried to kind of combine the images along kind of this rim line, this topographic line, so that there are still large swaths of this image where the illumination geometry is the same. And then you'll notice there are still shadows. There are still BSRs in here, and we'll let Shadow Chem fill in those details. All right. So step number one, image selection. So the first thing we did was we took all the images, we segmented them into a bunch of pieces and map projected them at 20 meters per pixel. This is mostly to make them easy to work with, avoid a lot of null data, smaller file sizes. And then we started to pull them into QGIS to kind of sort them. And we started with, subsolar longitudes that were similar to the longitudes of the region. And or had opposite subsolar longitudes, so we could kind of, illuminate the other side of like a ridge or a crater wall. And then we utilized, the PSR maps, the maximum pixel mosaics of all the images in the area, and then the average sun visibility maps produced with the LOLA orbiter laser altimeter LOLA team to assist with this. Overall, there was about an average of 300 images per site, which kind of worked out to about 650 different image segments. We didn't use every image segment from every image, right? Because a lot of them are like in shadow or there were better options. So another thing that we did to kind of help us sort out these images was we masked out the shadows. And this let us really see kind of what was under the shadows and some of the, the portions of the image segments with a lot of shadows, and kind of give us a first look at like what our final mosaics would look like. But you notice there's a lot of brightness differences, and at this point, none of the images have been controlled. So the next step was to do map projection and, actually control the images so that they're correctly aligned with the, 5-meter LOLA digital elevation models. So we map projected them at 1 meter per pixel, and then we applied these offsets that were calculated by Wegner et al. He has an LPSE abstract on this kind of brute force automated control method that we applied to each image. So basically this takes reference images that, we started at a point where we had a NAC digital terrain model, as well as a LOLA DM, and then you can take all the overlapping images, arrange them by subsolar longitude, and then, tie each image to the next image with the most similar subsolar longitude and kind of build out a chain of images. So this is an example of 66 images that overlap a single location at the Malapert site. So you can do this for several locations over an image, calculate an average offset, and then just apply that offset by modifying the upper left corner coordinates of your map projected image. While this worked for most of the images, when we were starting this mosaic team process, not all of the images were controlled with this like very automated method. It kind of just goes where it wants to go in the automation control process. So we did have to do some manual control, and then there's still a handful of images that just seem to refuse to want to be controlled automatically. So we did have to introduce this manual control step, which wasn't mentioned in the abstract, but we did have to kind of go back and do this to make sure that all the images had really good positional accuracy. So to do this, we just generated hill shades that matched the images kind of binned into 10-degree subsolar longitude bins. And then we just used Photoshop to kind of shift the images so that they aligned. And as a result, we ended up with these really nice subsolar longitude mosaics. Generally, they're bent into 10 degrees of subsolar longitude, but occasionally, if the images were kind of sparse, these bends can get up to like 50 degrees. And then we cropped these mosaics to the Artemis site boundaries, and we converted them all into 16-bit cubes. And then we pulled them into Photoshop, actually. And what we did is we very carefully identified, like, where should the transitions be between this subsolar longitude mosaic and this other subsolar longitude mosaic? And we kind of tried to draw in those boundaries so that there were lines of similar brightness, so there aren't these like startling differences between them, but also so that those transitions come at kind of intuitive places. So, you know, as we go over a crater rim, that's like a really good place to cut these lines. This is an example from Malapert Massif. This is one of the more complicated regions we've done so far. It has 8 different subsolar longitude mosaics and kind of colored the different polygons. You can kind of see where those occur. But this was kind of the last step in our process. There's a whole bunch of different applications for this, obviously morphological investigations, because we're releasing all the binned subsolar longitude mosaics. You could do a little bit of photometry, crater counting, also like hazard assessment. So here's an example where we're trying to identify a bunch of little boulders that wouldn't show up in a digital terrain model in an ACK image. So where are we on this? So we currently have roughly 4 of the 10 mosaics completed and released. 3 of them have been made with the process that I've described here. The kind of big one over the South Pole, Mark Robinson actually made using a pretty similar method. And that one is at 2 meters per pixel, while the rest of them are at 1 meter per pixel, but that one is also out on QuickMap. So where can you find these? Yeah, like I mentioned, all 4 of these are actually out as layers on QuickMap. The 3 that we made with this method are at 1 meter per pixel, and the other one's at 2 meters per pixel. And then in addition, all the 1 meter per pixel products are released to the LROC Planetary Data System archive, both the composite mosaics, but also the individual subsolar longitudes. So the links I provided here, like the names, if you go to our search interface, this will bring you to the composite mosaic, and all those link to the sub-mosaics, but they're all similarly named. It's just instead of 1 at the end for the composite, it's like A through whatever mosaic number we have. All right, and then what's left? We have roughly 3.5 of these released, if you count it as half released to get it out on QuickMap. And then roughly 4.5 are on line work, kind of trying to figure out those cut lines. It takes a little bit of time to really get something that makes sense and feels right. And then 2 are still kind of on that manual control step. And that's it. Thank you very much for your attention.